Welcome everyone to Foresight's Space Group. I'm really delighted to have Creon Levit here. Creon is chairing this group, and I've known Creon for quite some time. But we also met on accident on the way to the Eclipse on a plane again. And it was the best Eclipse I ever had. But I don't think I could have spent it with anyone better, because I think I really got the gist and the excitement that you conveyed to me about the Eclipse is entirely unparalleled. So I'm really excited that you will share some of that excitement with the rest of the group now. Please take it away.
All right. Thanks a lot, Allison. That was truly a delightful experience. And here's this is like from Wikipedia. This is a typical photo of a totality during a total solar eclipse. And I just want to say that it's okay. The human eye has a much greater dynamic range than any camera. And the natural world produces phenomena in a much greater dynamic range than a screen. What you see is a lot nicer than this, but this is pretty good. We'll talk about a lot of this. So we're going to do this as much as we can fit into the next 45 minutes or whatever it is. Talk about a couple of notable historical eclipses, including some I've seen and some I haven't. We're going to talk about how eclipses are predicted, because that's really interesting based on celestial mechanics and our modern understanding of the solar system. We're going to talk about eclipse prediction from a more historical cultural perspective, which I find fascinating. Then we'll go through a bunch of different types of eclipses, focusing on total solar eclipses. A brief slide on safely viewing eclipses. That's not so relevant right now because there isn't another one coming for a little while. We'll talk about some upcoming eclipses. Oh, this is obsolete. We'll talk about April 8th, 2024. We'll talk about it, but it's not upcoming anymore. And then we'll talk about some generalizations of the eclipse phenomena, such as transits and occultations. Now, notable solar eclipses that we are going to briefly mention. One is this one in 1919, which Sir Arthur Eddington set up 2 expeditions to test Einstein's theory of general relativity. We'll talk about the 1970 eclipse briefly. I was in this world, but didn't see it. My first one was in 1973. Where I went to Africa and saw it with many people, including these 3 well-knowns. A couple others that I've seen over the years listed here. And then the one Allison mentioned in Idaho, and then the one a number of us just saw in Texas, or in the United States. I saw it in Texas on my birthday. So I don't know how I'm going to top that birthday ever. Have a total eclipse on your birthday with a lot of friends. So this one that happened in 1919, there were 2 expeditions. I think one expedition went to South America, and one went to, I'm not exactly sure where it went, but on the African continent somewhere. And the purpose there was to test Einstein's general theory of relativity, which predicted that gravity bends light, among other things. And the idea here is, imagine this is the sun, and imagine this is a real star. And if the star is close to the sun, it's going to bend its light rays, shown here with this yellow non-straight light ray, if you will. And because of the fact that the light ray comes from a certain angle, the apparent position of the star will be here on the sky, even though the real position is here. And Newtonian gravity also predicts this, but it predicts a different amount of bending. So this is a picture of what you might expect. Imagine you had a grid of stars very far away, and you had a massive object between you and the stars. It'll act like a lens and move the real positions into these other positions. So that's what they were looking for. Nowadays, it's called gravitational lensing, and we see it all the time through telescopes. We see, here's an example of a relatively nearer massive spherical galaxy that is lensing a spiral galaxy that's farther away, that happens to be very close to it on the sky, although very far distant from it in distance. Lensing is a thing that we see all the time now, and it's just as predicted by general relativity. But back in 1919, general relativity was just a theory. And so Eddington and his crew set up these expeditions, and this is a picture of one of them. And here are 2 solar telescopes with these things called heliostats, which are moving mirrors that track the sun and keep the sun rays pointed into the telescope. And they had photographic film back then, emulsions, and they took pictures of the positions of the stars. They're easy to see in this negative image. These little lines are marks that they put where the stars are actually between those marks. And so they knew the positions of these stars from star charts taken at night. And then, some months later, those stars are now in the daytime sky and you could never see them. Hence, you could never see the bending of the light rays. You could never see the gravitational lensing because they're close to the sun, except during a total eclipse when most of the light of the sun is blocked. And then they were able to capture these stars on the film and compare the positions to the stars in the normal night sky when there's no sun around. And this is the result. So the dotted line here is the prediction from the Newtonian theory of gravity for where the stars should be. And this x-axis is the angular distance of the stars from the sun. And this is how much they're displaced from their positions when there's no sun bending the light. And you can see that so the prediction of Einstein's general relativity is this dark line here, and the measured least squares fit with zero intercept is this lighter line, solid line here, and a pretty good fit. Now, this is pretty controversial later on because, humidity and temperature can warp the film and cause these things to appear to move when they don't. And Eddington was like politically motivated because he was a pacifist and he was British, and Einstein was a pacifist and he was German, and they wanted to show German-English friendship after World War I. And so there's some ideas that maybe this data wasn't quite as good and it wasn't the slam dunk that it was in the headlines as proving Einstein's theory, but it was consistent with it. And then later on, once digital cameras came along, modern times, this experiment can be repeated with much higher accuracy and many more stars in subsequent modern eclipses. And the data is lining up pretty good with Einstein's theory. So Eddington was right. Einstein was right. And here's a sequence of successive tests of Einstein's general relativity with the error bars. And nowadays, with the modern eclipses, they've gotten the error bars to be really small. So it looks like Einstein was right. And there's many other tests of general relativity. This eclipse was in 1970. This is the path of, these diagrams show the path of totality in dark blue, and they show the path of the partial eclipse in light blue, different amounts of eclipse. So the path of totality is pretty narrow. This one passed, interestingly enough, over NASA Wallops Space Flight Center. Totality passed over that. So this is a launch facility that NASA runs, not quite as famous as the one in Florida, but they still launch from it. And here they set up all these sounding rockets, which are not orbital rockets, but they go way up into the atmosphere. And they were able to measure all kinds of changes to the atmosphere induced by the eclipse. There's another nice picture of these two-stage solid-fueled sounding rockets at NASA Wallops in 1970.
By the way, if you look on that map, you notice you can also fly your Learjet up to Nova Scotia and see a total.
Oh, okay, Brad, I'm going to have to ask for.
Oh, okay.
Sorry, I've got so much to cover. So yeah, my apologies. So this was the first one I saw. This one was the longest total eclipse for 3,000 years. It was in 1973. I think it's 3,000 years, like a few thousand on either side. So I got to see this one, my first one, the longest one I'll ever see. And unless Allison's friends can really get it together on the longevity. And I saw it just off the coast of Africa. And on this ship, I saw it from a ship, which was the second largest passenger ship in the world at that time. Now, no longer exists. And some of the, as I mentioned, some of the VIPs that they put onto this ship to get enthusiasm and sell a lot of tickets for this very first eclipse cruise, is now a common thing. It includes Neil Armstrong over here and Isaac Asimov over here. Here's Creon, young little Creon, 13 years old, with Isaac Asimov, who adopted me because we both had the same hair. And yeah, that was a trip. I'd read a lot of his books, and that was just a thrill. And we did also, they pressed the kids into service doing science experiments. So here's me and some other guy who is a buddy of mine on this ship. And we're setting up this is a big extendable pole antenna with a radioactive source on the tip and a picoammeter right here. And we were measuring the conductivity of the atmosphere before, during, and after the eclipse. So that was fun. It's a little kid citizen science kind of thing. This was what the deck of the ship looked like on eclipse day. And you can see you really have to be careful because you'd knock over a lot of cameras and maybe start a chain reaction if you bumped into something. There were a lot of astronomers on board, But this eclipse, the absolute longest total solar eclipse that anyone's ever going to see probably was the same one in Africa. But some astronomers managed to finagle a flight on the Concorde supersonic passenger jet, and they got the ability to put some holes into the fuselage and install optical windows and point their instruments at the eclipse, and they flew along the path of totality, and they got 90 minutes of totality. Now, this is never going to happen again, not in my lifetime, because A, there will not be an eclipse that is this long as this Africa one, and B, there are no supersonic transports anymore. There's no supersonic jets that are big enough to do this kind of thing. Here's the Concorde and the Russian supersonic transport. These have all been taken out of commission for not very good reasons, in my opinion, but whatever. Let's see, next eclipse I saw was, I saw it off the coast of Mexico, somewhere down here. And that also was from a ship. And there were two ships, sister ships, that went there to see it. And you can see it's a similar thing. On eclipse day, we rendezvoused and circled around each other and hailed each other. And there's similarly lots of telescopes with fancy mounting hardware that allows them to compensate for the rocking of the boat. Here's one of those compensating mounts. This is in the late 70s. This would never be allowed today, but these astronomers, they set up all kinds of gear in the fire escape stairwells. And so that was a different era. And this is what it looks like when you have a really clear view of the horizon during totality. You not only get the eclipse, but you get this kind of 360-degree sunset all the way around you. Oh, and here's an eclipse total eclipse viewed from the International Space Station, in the sense of this is the shadow of the moon here on the Earth. This is much later. Let's see, I saw this one in Canada. My family and I drove up from my childhood home in Chicago, watched this one just by ourselves on the side of the road in the snow. Here's a picture of recent and some forthcoming eclipse paths over the US. Here's that 2017 one that a lot of people saw, Oregon and Idaho and stuff like that. Allison and I saw it in Idaho, she mentioned. Here's the one that just happened on my birthday. A lot of people saw that. I saw it in Texas, but it was visible in a lot of places in the US. And here's one in 2045 that's coming. That's the next total one that's gonna, I guess this 2044 one will technically pass over the continental US, but this 2045 one is gonna go over some really good desert places, so good weather. Here's a map of since 2000 BC. So over 4,000 years of eclipse paths passing over the US. And you can see there's these weird patterns in places where more of them happen and less of them happen. So we're going to start talking about that. So here's the celestial mechanics of eclipses. So this is obviously not to scale here, but you have the sun, you have the moon, and you have the Earth. And the moon casts the shadow. And there's some places on the Earth at some times where the shadow of the moon lands and the moon completely blocks the sun. And that's called the umbra, and that's this dark place, and that's where totality will happen. And then this bigger circle at a moment in time is where the moon is, where if you're sitting in one of these places, the moon is only partially blocking the sun. So you get a partial eclipse. This is called the penumbra, this outer ring, which is much bigger. Now, you might think that since the moon goes around the sun every 28 days, since the moon goes around the Earth every 28 days, we should have a total eclipse once a month. But it's not so simple, right? Because the Earth orbits around the sun in roughly a circle, and that's called the plane of the ecliptic. That circle, that plane where the Earth's orbit is constrained around the sun is the plane of the ecliptic. But its orbit around the Earth is not in the plane of the ecliptic. It is tilted with respect to the plane of the ecliptic. So we do not get a solar eclipse every month. So here's a picture of that. There's the moon's orbit in blue, and it's orbiting in a different plane than the Earth's orbit around the sun, which is in gray. And because these planes are not the same, it's more complicated. So there's this thing called the line of nodes, which is basically where the moon's orbital plane intersects the plane of the ecliptic, where the blue plane intercepts the gray one. It intersects it, and that two planes always intersect in a line. And this line of nodes is basically fixed with respect to the fixed stars, because the moon orbits around the Earth, and the plane rigidly goes around the sun. It's constant with respect to the fixed stars. Most of the time, the moon's shadow totally misses the Earth, and the Earth's shadow totally misses the moon. But once in a while, you get a new moon where the line of nodes, the intersection of these two planes, happens to be pointed at the sun. This happens near the equinoxes. It's eclipse season. Doesn't always happen because the moon can't be too far away or it gets out of alignment by the time the moon comes around. But if you get a new moon near one of the equinoxes, you're going to get a solar eclipse. And if you get a full moon near one of the equinoxes, you're going to get a lunar eclipse. Here's another illustration of that, kind of trying to show these planes going, lunar orbit going around the sun, and in the summer and the winter, the shadows of the moon and the Earth miss each other. But near the equinoxes, the shadow of the moon can actually intersect the Earth. The important thing is that these planes only intersect along the line of nodes. And the line of nodes only intersects the sun near the equinox. Okay, so here's a diagram showing a calendar of a bunch of years, and you've got your full moons and your new moons plotted and your line of nodes plotted, and where they intersect, you get eclipses. So these little lines are the places where you can get eclipses, total or partial, solar or lunar. So there's obviously like a complicated periodic frequency happening here because you've got different motions that have different periods, and it's only when they come into alignment, literally, that you get the eclipse. So what this means is that eclipses have a regular pattern that's complicated. So the main pattern people know about or talk about is called the Saros cycle, and it's 18 years roughly. So here we have the 1901 eclipse, and here we have the 1919 eclipse. These are totality paths that Eddington went to, and then 1937. And then these are all 18 years apart, 1937, 1955, 1973. That was the Africa one that I saw, 1991. And then other ones, including this 2045 one that we'll talk about. But there's multiple Saros cycles going on at once, and viewed on a round Earth, maybe it makes a little more sense. This is that same, no, this is different Saros, but you can see that there's regular patterns, except the Earth is, of course, rotating once a day. So these things, it happens at different places on the Earth's geography because there's yet another periodic motion, which is the daily rotation of the Earth. Yeah, and then there's longer cycles too, like this. So essentially, sometimes the Earth, everything lines up and you get an almost repeat. So this is, let's see, 2024 to 1970, that's 54 years. So there's a 54-year cycle where the paths of totality almost go identical, very close. So this was that one in 1970 where they launched those rockets that I was talking about. And this is the one that just happened on my birthday. And they're part of the same cycle, but it's not a Saros, it's a 54-year cycle. And there's all these weird names for these cycles. So let's see, the 54-year, do they even listed here? Years. Okay, maybe 54-year cycle is the exoligmos. That's the name of that cycle. So there's all these different cycles with different durations from a few years to hundreds of years that are useful for predicting eclipses. So who figured all this stuff out? Well, you might think it was the people at NASA and places like that, or maybe the scientists back in the pre-computer era, but who were really good at calculating. But it turns out the ancients knew about this. This is a famous thing called the Antikythera mechanism that you may have heard of. This was found in a shipwreck from, I don't even know. It was basically like right between the kind of in the transition period between the Greek and Roman empires, I think. And they found this thing. It was almost like alien technology, if you will, that comes out of this shipwreck. And it was just ridiculously precise with machined gears out of metal, multiple gears, all these complex fasteners and threaded inserts and things that we would think of as quite modern, but this is thousands of years old. And this turns out, after they spent some time reconstructing it, these are just the gears and fasteners. But when they reconstructed this mechanism and figured out all the clockworks, they figured out that sure enough, this is a rendering of what it may have looked like in its full glory. It was a little astrolabe. You turn the crank, the planets and the moon and the sun all move around, And it, among other things, predicts solar and lunar eclipses. It also predicted when they were supposed to have the Olympics and the positions of the planets. So this was some kind of, it's speculated what it really was. Was it a vanity project? Was it a kind of a store of wealth, or a exhibition of intellect? Or not clear why it was made. Not clear. It's clear what it does, but it's not clear why they made it. But long before the Greeks, people were building the instruments, if you will, to predict eclipses, as well as things like solstices and equinox. And this is one of the, these were megalithic structures. Stonehenge was one of them. It was pretty well established once they started reconstructing, doing some digging around Stonehenge and realizing that it was more elaborate than they had initially thought. Some very smart people got involved. Fred Hoyle, the famous astronomer and cosmologist, and this guy Hawkins, and they both independently came up with they both independently convinced themselves that Stonehenge was basically built to predict eclipses. And they figured out how it would work. Like at the solstice, you'd move one of these markers, and then every month you'd move one of these other markers. And then when they lined up, it was like the sun and the moon were going to line up on the solstice, and they knew this was coming. So God knows how they figured all this out in the Isle of Britain with the weather that they have, but they did. They figured it out, and they built this thing with a great effort. Oh, here's the young man, like teenage high school Creon at Stonehenge. Back when they let you actually get up and touch it. These stone circles are all over Europe and in the UK, and like literally thousands of them, not all as elaborate as Stonehenge, but these people were serious about calendrics. I also went here. This is in Ireland. This is Newgrange. This is even older than Stonehenge, and apparently was also used for similar purposes. And then when I was there, I bought this book, which is an amazing book that talks about this whole civilization and how they built these things and why they built these things and what the dynamics of the civilization were. Very interesting. Don't have enough time for it. And then coming forward a few thousand years, many thousands of years, in order to predict eclipses accurately, like down to the second, which you can do now, one of the things you need to know is the distance to the moon with pretty high accuracy. So one of the things they did for the Apollo missions, on several of the Apollo missions, they left on the surface of the moon these retroreflectors, which are like fancy versions of bicycle reflectors, where whichever direction the light comes in, it comes back out in the same direction, just using simple optics. And now it's a whole other thing. Retroreflectors are amazing, but they left these things on the moon, and then they started bouncing lasers off them from the Earth, and they could, by timing the round trip of the laser pulse, they could get the distance to the moon to extremely high accuracy. Okay, ratcheting back a moment to what we were talking about with the celestial mechanics, I'm going to show a brief little animation here. This happens to correspond to the 2017 eclipse, I think, but it doesn't matter. They're all like this. And this is to scale. So here's the Earth and the Earth's shadow, and here's the moon and the moon's shadow, and the moon and the Earth are the correct size and the correct distance to be at scale. And the sun, of course, is like 400 feet off to the left in this diagram, and huge. So we're going to watch this happen. Remember, they're not in the same plane. So here's the moon orbiting the Earth, and there's its shadow, but you see the shadow is missing the Earth because the moon's plane and the plane of the ecliptic are not the same. So now it goes and goes. The Earth is spinning. It's going around the sun, and eventually the moon happens to pass through the line of nodes, and so its shadow falls on the Earth, and there it goes, sweeping across the Earth, and that was the eclipse. So that's just to show you what's going on at scale compared to those cartoons. Oh, let's see, partial eclipse. What are we going to 2017 partial eclipse. I'm not quite sure why this is in here, but partial eclipses are a thing. Many people have seen them. And you ask people if they've seen a total eclipse, and they'll be like, oh, I think I saw one when I was a kid. And right away, that was a partial eclipse. Because if they've seen a total eclipse, it's a completely different thing. So partial eclipse, lots of people have seen those. This is time exposure over the course of 2 or 3 hours. Here we are at Planet Labs a number of years ago looking at a partial eclipse. You have to look through eye protection because you're basically just staring at the sun. Oh, here's a beautiful a photo of a partial eclipse using a hydrogen alpha telescope where you could see all this detail on the surface. The sun is basically the most complicated thing that isn't biological life in our solar system, because it's always changing every day. And as we know, with those recent auroras and stuff like that, it has a very active life. You can also view a partial eclipse through a salad strainer or pasta strainer, and you get all these nice, the pinholes give you all these nice little crescents. The trees also give you nice little crescents. This is one of the more striking things in the solar eclipse, because normally the trees make this dappled light, which is basically circles, because the sun is a full circle, and no one notices because that's how it is all the time. But during a partial eclipse, all of a sudden it starts to look like this. Here's another nice tree shadow on the side of building. Oh, let's see.
Okay.
Here's me in Palm Springs just a few months ago during the annular eclipse with my colander.
Be cool.
And then going over the trees. Enough on that. Oh, and here's a really fun one. Here's a partial eclipse with a sunspot, and a transit of the International Space Station. And there's this famous astrophotographer, a brilliant guy who like goes to the exact right spot on the Earth, which is usually the middle of nowhere, and at the exact right second takes these pictures where you have like the transit of the space station, some celestial phenomenon. If any of you are Star Wars buffs, I showed this to a friend of mine back at NASA some time ago, and his remark was, "That's no moon, it's a space station." Anyway, so the thing about it, it's even more complicated than I said, because the moon's orbit around the Earth is not really a circle, nor is the Earth's orbit around the sun. They're slightly elliptical. So what that means is that sometimes the moon is closer to the Earth and looks bigger, and sometimes the moon is farther from the Earth and looks smaller. And so that means that sometimes when the moon is farther from the Earth, it doesn't actually cover the whole sun from the point of view of the Earth. And in that case, even if the nodes line up everything in the equinoxes and the planes of the orbits line up, the moon does go directly in front of the sun, but it's too small, quote unquote, to cover the sun because it's too far away. And then you get an annular eclipse, which is fun, but nowhere near as fun as a total eclipse. This is still too bright to look at with your naked eyes, unless it's happening at sunset. And this you can look at with your naked eyes. It's so dark that the stars come out. So I didn't see this, but this is a time exposure of an annular eclipse at sunset. So that's quite something. You also, of course, have lunar eclipses. And if you think about it, this makes sense. Lunar eclipses always happen either 2 weeks before or 2 weeks after a solar eclipse, because everything's still lined up. And now the moon moves 2 weeks later instead of between the sun, the Earth is between the sun and the moon. And then the Earth's shadow falls on the moon. And lots of people have seen this. Now we're going to go back to total eclipses for a moment. You see how I'm on time. Oh boy. And so we got this is called first contact. Let's see. First contact when the moon just starts to bite a little bit into the sun. And then it progressively covers more of the sun if you're on the path of totality. Then you get what's called second contact, which is where the last bit of the sun disappears behind the moon. This is also known as the diamond ring. And then you have totality. And then you have third contact when the sun starts to poke out from behind the moon, obviously on the opposite side of where it disappeared. And then you're back into the partial phases. And fourth contact is when the moon completely leaves the sun. And so that's totality between second and third contact, or between the first diamond ring and the second diamond ring. And we're just going to show some more photos. Brad takes photos like this. He's got an amazing rig and amazing skill in this area. And I presume that your background photo is one that you actually took, Brad. But anyway, so here we have the diamond rings. This is just usually a few seconds. And then we have totality, which is usually a couple of minutes. Diamond ring is named so for obvious reasons. It doesn't really have these spikes coming out of it. That's just diffraction from the diaphragm on the camera. This doesn't actually look like this with spikes. This is just a camera artifact. Totality looks like this. This is a high HDR photo where they've combined several photos with different exposures, but your eye can actually see this. So these are called coronal streamers, and they're different during every eclipse. These are prominences, these pink things leaping out from the edge of the sun, and they're actually pink. And here's another neat time exposure. Again, this partial was taken with extreme dark filters over the camera, and then the filters are removed for the total phase. Here's what totality looks like. The sky is actually darker than this, but the sun is black, and you can see the stars and planets come out, and you can see this 360-degree sunset that I talked about if you got a good horizon. It's really quite astonishing. It gets cold and dark, and the stars come out in the middle of the day. Some of this solar, the chromosphere is this colorful part of the sun that you can really only see during certain phases of the eclipse. And the corona is much fainter. The corona is in the actual, see the corona during the day. But during an eclipse, you see the corona. And all right, we're not going to talk daily speeds. And now it says my internet. So this is a very quick time exposure of the last little bits of the sun disappearing behind the valleys of the moon and blocked by mountains in other places. Again, these bright spots are where the sun is poking through the valleys on the limb of the moon. And these are prominences in the chromosphere. Second diamond ring, I presume. Again, the sun starts peeking out through the valleys and then eventually peeks out completely over the lunar limb. These are, whoever takes these photos is like very serious. Tracking time exposures, variable exposure. This one is insane. Beads as the sun slowly emerges. If you corona, they used a gradient filter so the dimmer parts of the corona are exposed more than the brighter parts of the corona. But your eye can see this, especially during an eclipse, this April 8th one, or the one I saw in Africa, where a very active sun, we're near solar maximum, or close enough to it that the sun is really active, so it's shooting out all these things. Other times the corona is more like this, like uniform. This is an extreme kind of retouched gradient filter. You don't actually see the coronas going. The coronal streamers are not visibly that far, but they do exist that far. Oh yeah, this is just some Planet Labs stuff. We have to track the activity of the sun over the course of many years. And this is some years ago, but you can predict whether the sun's going to be active or not. All right. Last multiple exposure with gradient filter. So you can actually eclipse pretty well, even if there's some cloud cover. In some ways it's better. The 2017 eclipse that we mentioned before, whenever you're going to go see an eclipse, look at these charts that show the cloud cover historically for that day at various paths along the eclipse. So let's see. I was like, I'm going to Idaho because it looked like pretty low historical cloud cover. Although I guess we were in the Snake River. Yeah, the Snake River Plain. That's where we were. And so you stare at a lot of historical cloud maps. Here's the eclipse path. Here's the historical cloud cover on that day. Another cloud map made by our friend Matt Hancher from Landsat. This is a great map. This is for the 2017 eclipse. This is past week Google search interest on solar eclipse and where those search interests came from. So they obviously came from near the path. And I saw this eclipse with two of my favorite women in the world. One right here, you may recognize, and my mother, who's off camera at this time. Oh, let's see, how much time do we have? All right, we're going to just watch a few seconds of this. If we share it, let's see. Can you see YouTube? Can anyone see YouTube here?
No, not yet.
Your
right.
bandwidth is having problems, so I'm not sure how well this will work.
Yeah, I'm going to skip it. If there was an eclipse about to happen, I would go through all this safety stuff. But the one thing to remember is to try and see it with someone who knows what they're doing, because the most tragic mistake people do is they hurt their retinas because they look at the wrong time. But that's pretty uncommon because you have an instinct to not stare into the sun. But during the totality, you can stare at the sun without any eye protection. And the tragic thing is when people go all this way to see a total eclipse and get all psyched up, and then they keep their eclipse glasses on during totality and basically see nothing.
Pardon correction, Creon. I don't think it's number 10. I believe it's
you can use number 10. It's not as comfortable as number 12.
I've used 12, and 12 is too bright. Anyway, okay. But 14 is the normal recommendation.
Oh, okay. Sorry, I should fix that. Yeah, I use the trick. If you tilt the glass, it gets a lot darker because the rays have to go through a lot more distance. So you can adjust for it by tilting. But yeah, thanks. I'll fix that,
The,
Brad.
the trick I use is I don't even watch the partial eclipse.
I keep one eye closed or covered during partial eclipse so that during the total eclipse, I have two different dynamic ranges. But that's subtle stuff. Let's see. I went to this one in China in 2009. This was a nice shot that a friend of mine took of a partial phase in the parking lot of the hotel where we were staying. We watched it from the balcony of the hotel. Oh, that's a young Chris Kemp, if anyone knows him. And it was like really hazy and cloudy on the.
Now you've frozen for a while. I don't know if you hear us.
Well, it's a nice shot to look at while we wait for him to come back.
It was very hazy in China. It rained in a lot of China, actually. I saw this in Eniwetok where it was clear.
Oh, Creon, are you back?
Wired Ethernet if you're presenting, folks.
Let's give him a moment.
No, I think we may have lost Creon entirely.
Brad, did you want to make any additions here?
He was talking about the 2009. Oh, no, he's back now.
Hey, Creon.
That was Starlink. When did I drop out?
With a relatively hazy photo of you, of the camera pointing, I think, in China at the river.
Oh, okay. So let me see. Let me get back to Keynote.
Oh, yeah. Starlink's upstream is not that great.
No, it was just a dropout. It was clear to keep launch from the south.
Missing bird.
Um,
No, you've been dropping out pretty frequently, and now you've
All right. So, okay, let's see. Oh, this is just a nice little. We'll see if this goes through or not. I guess this is the 2017 one, but it's nice. It's just the path of totality and the path of partiality.
No, that's a 20.
Oh, this was the annular eclipse that just happened. That one where I was in Palms. Yeah, I think this was the annular one though that happened. Whatever, I don't know how many months ago. Anyway, and this was a great shot that a friend took from Planet Labs. I don't remember where he was. He was actually on the path. The Palm Springs stuff I showed walking around the vegetable colander was not on the path. Again, annular eclipse at sunset. The eclipse on my birthday and the path there. Oh, look, that's a nice animation of the April 8th eclipse. Where did you see it, Brad?
I was outside of Sherbrooke, Quebec.
Oh, nice. Okay, so it makes landfall in Mexico.
I had hotel rooms in Texas, by the way, but I gave them up and flew to the east instead because of the rain forecast for Texas.
Yeah, so let's talk about that. We were studying the clouds and we were near Austin and it was like iffy. The clouds were like 50% probability, whatever that means. Does that mean 50% of the days it's cloudy or 100% of the days it's partially cloudy? It's hard to know. Another cloud map from Hampshire. I studied Landsat maps. I'm like, okay, so Austin's about here and this is several years ago and this is another more recent year and another more recent year all on April 8th and another more recent year. And it was like, the prospects looked okay, but not perfect in Texas. Looked like we might have partial clouds. We'll skip this. So we all gathered, a bunch of people together in Texas. I think Luke's on this call. Both Luke and Dan Barquet are ex-Planeteers. We gathered at my friend Peter Wang's ranch, Allison's friend too. And he had many telescopes, including this recently completed 28-inch Newtonian. And it was beautiful. It was quite clear, especially that night. And so we looked with the image intensifier through his telescope, the big one, and you could literally see this with your eye. You could see, I saw dozens of nebula that I've never seen my eye before because he has this image intensifier rig. And this was just with a cell phone taken through the eyepiece of his telescope. But that morning, it did not look good. Lots of clouds. We decided to go and we hightailed it northwest, drove for about an hour and a half, landed at this okay viewing spot, State Park. So here's our crew, a lot of friends, kids of friends. And we saw it. Someone took this from our group with their new iPhone. So that's pretty good. A little bit camera shake, but we got to see it, even with some scattered clouds. Right around third contact, when the sun starts poking out again, this was from my bad iPhone camera, and you could still see what was going on. In fact, the clouds are nice around the diamond ring because you can look for longer. And here's a picture of that eclipse passing over Texas from space. This is taken by the Discover satellite, which always has a full view of the Earth because it's sitting at the Lagrange point. L1 between the sun and the earth. So it always has the full. And here's a. I'm curious why the moon isn't itself visible in this photo, but there's probably some fine celestial mechanics there that I don't quite understand. Because the moon does come through occasionally to discover field of view, and it does cover the earth. It does block part of the earth. Next eclipse that I'm probably going to is in, is it 2027? Yeah, I think so. It's August 2nd, 2027, I think. And it passes over you can see it passes over North Africa and then actually a little bit over Spain. And so it's pretty long. It's the longest one for 300 years. If you're willing to go to Benghazi, which I'm not, or if you're willing to go to okay, everyone in the world is going to converge on Luxor or Egypt because it's the tourist attraction. It's this giant temple, and it's going to be in the path of totality, and it's the longest totality for a very long time. I'm thinking that we're going to go to either Gibraltar or Morocco. I know it's shorter, but I don't really want to go to Egypt with a million other people. I don't particularly want to go to Saudi Arabia, although that's another possibility, depending on what's going on.
Fewer clouds in Egypt, but also 105 degrees average temperature at that time of year.
Yeah, but I live in Palm Springs, so that'll be cool for August. Yeah, so I'm thinking either Gibraltar or Morocco, both places which I've never visited and would like to. And then last eclipse I'm going to talk about, oh boy, okay, we have 5 minutes. Last eclipse I'm going to talk about is when is it again? It's in 2045, okay? Now, the interesting thing about this is it's the next big one that comes over the continental US. But the interesting thing is it's in August 2045, mid-August, and it passes over Black Rock City. And it passes over Black Rock City 2 weeks before Burning Man. So they're going to presumably move Burning Man 2 weeks earlier in 2045 when I'm 85 years old. And I'll be out there at Burning Man. I'm not going to miss that one. I don't go to all Burning. I only once every few years go to Burning Man, but I'll go there for that one if I can. And that should be awesome. Okay, so speaking of future eclipses, the moon's orbit is getting slowly farther and farther from the Earth. It's only 6 millimeters a year farther, but it is getting farther away. And that means eventually it will get so far away that it will never cover the sun during an eclipse. It'll only get annular eclipses at best. This will take 200, 300 million years, but it will happen. Now, one interesting thing about lunar eclipses, so in a lunar eclipse is where, as we mentioned, where the Earth's shadow covers the moon, usually 2 weeks before, 2 weeks after a solar eclipse. Now, but if you were on the moon, it would look like the Earth is eclipsing the sun. The Earth is blocking the sun. And sure enough, this has been imaged. This is from the Japanese Cayuga Lunar Orbiter Probe. And here it imaged, here's the horizon of the moon. But here it imaged, it was in the shadow of a lunar eclipse, but it was on the moon. So what it sees is the Earth covering the sun. Now, the Earth is much larger than the sun from this vantage point, but nonetheless, the atmosphere of the Earth refracts the sunlight and you see all this stuff. So that's been imaged. Other celestial bodies can come between the Earth and the sun, not just the moon. Here's transit of Venus. I saw that with some friends. This was, 12, 13 years ago. Transit of Venus is very rare. You only can see usually 1 or 2 in your lifetime. So we hightailed it up to Mount Wilson and saw this. Here's Mars occulting a star. Forget which one. These things occasionally happen, and they're used to try and probe the atmosphere of the planets. As the starlight goes through the atmosphere, you can see what petrol lines are quenched. Here's the moon occulting Mars. These are like eclipses where things just line up exactly right. I saw this through my little telescope. I didn't take this photo, but I did see it. I also saw this, the moon occulting Saturn. Saturn dips behind the moon. This happens like every 6 years or so. And then Saturn, an hour later, pops up on the other side of the moon. It's really beautiful. Really beautiful. And here is, speaking of Saturn, here's an artificial eclipse of Saturn. And what I mean by that is the Cassini probe, which orbited Saturn for many years, took this photo when Saturn was blocking the sun. And so what we see is scattered light from Saturn's atmosphere. We see scattered light from the rings, and we even see the F ring, which is super faint and hard to see. This was a big operation they did and a very beautiful photo. It was like, I don't know, many dozens of images that they stitched together. And you can even see, I think, doubly scattered light right here, off the rings onto Saturn and then back. I think, something like that. Or maybe off the atmosphere and then off the rings and then to us. And then last but not least, here's New Horizons imaging Pluto occulting the sun. So this is a total solar eclipse by Pluto that you see from this wonderful mission, New Horizons. Planets can eclipse other stars, and now we look for transits in front of other stars, looking at very subtle variations in their brightness. And from that, we can determine things like the size and period of extrasolar planets. This is data from the Kepler mission, and there's also the TESS mission. This is a thing now. And then I'll just say that eclipse is a metaphor in addition to being historically and astronomically and culturally relevant. It's a metaphor, darkness at noon. Now, this is a book about an eclipse called Darkness at Noon, written in 1806, but there was a more famous Darkness at Noon written by Arthur Koestler, which is a novel about the Bolshevik Revolution, named Darkness at Noon for obvious reasons. So anyway, eclipses, they're amazing. They take you to places you might never otherwise go. You meet all sorts of people and have a shared experience, which as far as I'm concerned, is like literally the greatest show on Earth, only available from Earth. It's very unlikely that the moon and the sun would have exactly the right angular size in the sky to make this phenomenon. But it does, at least for the next.
Which is why, Creon, it's quite odd you've not mentioned the 2026 eclipse coming, which is the next one, which will be short at just under 2 minutes, but shorter is in some ways better.
Oh, okay. I can certainly go along with that since I'm short. Anyway, yeah, I didn't mention 2026 because I'm probably not going to go. Maybe you can convince me to, or maybe you can get me a seat on a plane. I don't know. We'll see what happens. Okay, that's all, folks. We can do questions now or end it. I'll leave it up to our organizers.
This is fantastic. Thank you so much, Creon. It was really beautiful. I love the Saturn one. I think, this is off. I love the Saturn one in particular. I think it was fantastic. We are at time. Maybe we do one question. I don't know if you have time for one, and then we'll.
Yeah, I have time. Let's see. Do I have anything? I don't think I have any. No, I don't have anything hard. I have no hard deadline, so we can do a question or two.
I have another one in a meeting in a bit, but that also shouldn't stop you from taking more questions. I definitely want to make sure that some other folks also get to share. Does anyone have a question, comment? I absolutely love this one, especially all of the young Creon photos in front of Stonehenge. Those are my favorite.
Eventually, there'll be young Allison photos as well.
One day, yeah.
No,
Brad,
she's got a picture in the attic.
Yeah, apparently. I've been accused of that very same thing. But
Catherine definitely has a JPEG in her digital attic. Keeps her young. There's an interesting question because, as you said, it is an unusual coincidence that the moon and sun are the exact same size, and the Earth, angular size. And the Earth is the only place we know that happens. There was even a science fiction story that imagined that aliens might be coming to Earth because it was unusual in the galaxy in that way.
That's what I say. When you meet quote unquote people at a total eclipse, you should look very carefully and see if they're actually people, because they may have come from very far away.
Some of them have come from far away. Anyway, so the argument says that a long eclipse is in its sense bad because the moon is significantly larger than the sun during a long eclipse, and during a short eclipse, it is exactly matched. The Spanish eclipse, which will take place, it goes to Iceland, but I would recommend Spain. It will be at sunset in Spain, lasting a little under 2 minutes and crossing from the northwest and ending up over Ibiza. And so the shorter it is, the more spectacular it will be, although for less time. And that is
okay. But having said that, Brad, I will go back briefly to another picture, which I skipped, which basically points out that there's another option. If what you mean by shorter is better is you get more transients, you get more prominences, you get more diamond ringy things, and you get more edge effects, if you will.
Well, effects are why you go.
Yeah. Okay. So if you So this might be of interest to people. So here's a graph that shows how the length of totality versus how far you are from the center line. And it turns out that there's a spot where you get like half as much totality, but you get way more edge effects because this other curve is how many edge effects you get. So I did an expedition to Turkey with the late great Tom Van Flandern, where
I went with Tom as well. Tom's the high priest of this.
Did we meet each other on that trip?
No, I wasn't on that one. It was a different one.
I went to that meteor shower one he did as well. But anyway,
Tom was a bit crazy.
Yeah, I know, but I like that.
Yeah.
That's why I like you. Anyway, so yeah, you can go to the edge and you get a shorter eclipse with more edge effects. But that's all I had to say about that.
Yeah. Now, this picture that you'll see here that I put as my background, it's not a real picture. It is the combination of second contact and third contact. So you see all the prominences. So this is what you would see if you were watching a very short eclipse. You'd see it for a very short time, but it would be a little more spectacular.
That's cool.
Looks awesome. I just found out that the one in 2026 that's going over Ibiza is also going over my mom's house on Mallorca. So we should go there.
Well, Allison,
All right, that's the plan.
The great risk of Mallorca and Ibiza is it will be right at sunset there. And that means it could be very spectacular, but also there's a higher risk of clouds at sunset. So you'd want to be looking at the weather models, which is what I did. I was looking at 7 supercomputer models to figure out where I was going to be. And I got one of the places with no.
So,
by the way, speaking of weather, on the recent one on my birthday that just happened, we had our own weather guy. We had Johan Mate with his Atmo models telling us where to go.
In my 2010 eclipse, which I saw with even more famous people than Neil Armstrong and Isaac Asimov.
I don't think there's more famous people than Neil Armstrong, but go ahead.
Yeah, no, you're right in many ways. But anyway, we had the CEO of Weather Underground on the trip as well, among other things. And we nonetheless, we picked the pace with the best probabilities. But here's something to note for the future. Supercomputer models of the weather will continue to improve. And by 2044 and 2045, you will probably have a very precise weather model many days out.
So I can't imagine Burning Man getting clouded out, but I suppose it could happen.
But anyway, it will not be left to chance by a few decades from now.
All right.
Well, thank you so much, Creon. This was absolutely fantastic. I really appreciate it. And I learned so much and also just was, pretty stunned by the imagery. That was really beautiful. Thank you.
One does one's best. All right. Thanks, Allison. I'll see you next time.
Thanks, everyone. Bye.